So in this example, let's graph an equals n over n plus 1. Okay, what do I get? I mean, you could go back to beginning algebra. Your input is n, your output's an. What do I get when I input 1? I should have gone even higher with this scaling. Here, let me make this guy 1 here, so that this guy is a half. Okay, and then what do I get when I plug in 1? Half, right? And then what do I get when I plug in, say, 2? 2/3. 3? 3/4. Let's just do one more. 4? 4/5. So I get these values. At 1, I get a half. At 2, I get, well, 2/3. So it does go up a little bit, actually, but not a lot. So 2/3, 0.6 repeated. 3 3/4. So there's the 3/4 mark. A little bit higher. And then 4 4/5, just eyeballing it. Is it ever going to, let me erase that. Just put it a hair below 1. Okay. Is it ever going to get to a height of 1? No. So if I put in kind of a horizontal line here, it's never actually going to reach that, is it? The outputs, I mean. The height value, the outputs of those points that I'm plotting. Never quite going to reach that horizontal line at a height of 1, right? What does that mean about the limit of an as n gets bigger? It's going to get closer and closer to 1. These height values will get closer and closer to 1, but never actually get there. So what I'm trying to do is kind of implicitly define with this graph the idea of a limit. And whenever we talk about limits of sequences, it's always just as n gets bigger, so as n goes to infinity. So I'm trying to get across this idea of a limit. And it really is the same idea of limits at infinity that you've looked at in the past. So what is the output of n over n plus 1 approach as n goes to infinity? Well, it sure looks like it's 1. That's note number 1. Note number 2, in general, if an approaches a fixed number, L, as n goes to infinity, we write the limit as n goes to infinity of an equals L. No big surprise there, right? It's the same notation we've used in the past, except instead of f of x, we have a sub n. We say an converges to L. Otherwise, we say an diverges. It's worth putting that terminology in bold print, probably. And then if you'd like to use the epsilon idea, we don't need a delta here, but if you'd like to maybe have a more rigorous definition, which we won't resort to very often, if at all, in this class, but it's nice to get a hint of what the more advanced mathematics will put you through. Number 3, if you let epsilon be greater than 0, so we remember from Calc 1, we just think of epsilon as being a very tiny positive number, right? And suppose an arrow L, so this, when you see this notation, it's shorthand for saying the limit as n goes to infinity of an equals L. They both mean that thing in purple right there and an arrow L mean the same thing. It's just an arrow L is a shorter, less to write down. So let's let epsilon be greater than 0, and suppose the limit of an as n goes to infinity equals L. Then that notation, or that idea that an approaches L as n gets bigger, means that for large enough n, you can get an arbitrarily close, in other words, within epsilon, to L. And so in pictures, what does that look like? Well, I've got a couple stragglers down here that I didn't erase. Hold on. Okay. So in pictures, here's what that means. Let's say you pick an epsilon, just some number greater than 0. It could be super duper tiny. It could be microscopic. But, and we have some an that converges to L. What that note in number 3 means is this. If you create an epsilon band around L, so what we're saying is this. The outputs of AN, early on, the outputs of AN don't have to necessarily lie within epsilon units of L. So, early on, maybe A1 is here, maybe A2, you could plot it to be up here, maybe A3 is down here. But eventually, if you get N big enough, the fact that AN approaches L as N goes to infinity means that eventually your graph, your outputs of your graph, height-wise, will be in between these two purple lines because they indicate the interval from L minus epsilon to L plus epsilon height-wise. And if we know AN is approaching L, we know that AN has to get inside that interval for large enough N. And eventually, the outputs will start, if they don't have to alternate between being above L and below L, but that's why I'm drawing it here. Eventually, absolute value-wise, they're going to get closer and closer to L as N increases. So graphically, that's what's happening. That's what it means to say, to try and relate the limit definition here to the epsilon definition that you learned in Calc 1. We don't need a delta here. We can do it just with epsilon and the idea that N, the input's getting bigger. So here's how I would think of it. I actually like my second statement better than the picture. For large enough N, you can get AN as close as you want. That's what arbitrarily close means to L. You could think you have this person fooled. What if we make it like the Planck constant, which is some extremely small number? Well, if AN truly approaches L, there's going to be an N big enough that you'll be within the output, the height value of AN will be within that Planck constant of L, if AN truly converges to L. Here's a carryover from Calc 1. Remember the squeeze theorem? So let's let the limit as N goes to infinity of AN equal L. Again, that's the same thing as saying AN approaches L as N goes to infinity. So the as N goes to infinity or as N gets bigger is implied when you use the A sub N arrow L notation. So let's suppose the limit of AN equals L and the limit of BN equals L as well. That's what I'm saying in this first sentence here. And then suppose that Cn really is in between AN and BN for N bigger than some constant M. You can't guarantee it if N is less than, you can't guarantee that inequality that Cn is between AN and BN if N is less than some constant M. But let's say that this is true, that Cn is between AN and BN for N bigger than M. Then what do you think we can say? If the limit of this guy, let me draw it this way. If AN approaches L and BN approaches L, and for large enough N, Cn is always between AN and BN, what do you think Cn is going to approach? L. That's the squeeze theorem in sequence notation or lingo. So we could say, using the limit notation, the limit as N goes to infinity of Cn equals L. Number 5, the limit laws from Calc 1 do hold. So what do I mean by the limit laws? So like the limit of, let's say, a sum of two sequence formulas or a difference, what would that equal? Assuming both converge, assuming both AN and BN converge to a number. Now, what do I mean by that? When I say assuming AN converges to a number, that's the same thing as saying the limit of AN as N goes to infinity equals a number, right? So assuming that both AN and BN converge to a number, then the limit of the sum is the sum of the limits. That's one of the big limit laws you learned last semester. And we're saying all of those limit laws that you learned last semester hold. So you could change You could change this to times, right? You could change the operation times. You have to be careful, but you could change it to division as long as you don't get division by 0, right? Yeah. So you do have to be careful when you're using division. But all of those limit laws that you learned in Calc 1, they hold. There's no reason why they wouldn't hold. A(n) and B(n) are just functions, like in Calc 1, right?